Let us first recall the statement of Nakayama's lemma and then prove it. Let A be a commutative ring with identity. And M be a finitely generated A module if I is an ideal contained in Jacobson's radical of A. This is Jacobson radical of A. Such that I m is m, then m is 0. Proof is a straightforward application of the result that we proved in the last class. Suppose I m is equal to m, then you can think of the identity map taking phi to be the identity map so phi of m is m, which is I m. So, phi of m is contained in I m. Therefore, by the result that we proved yesterday, there exists, we obtain an element x in A such that 1 minus x or x minus 1 belongs to I and x m is 0. Right. Now, I is contained in the Jacobson's radical. I is contained in Jacobson's radical. What does that mean? Yeah. So, we proved this characterization that x is in Jacobson radical if and only if 1 minus x y is a unit for all y belongs to A, right. This is something that we proved quite early in the course. So, using this, what we get is therefore 1 minus x, taking y to be equal to 1. 1 minus x is a unit in A, which implies x is a unit in A and x times m is 0 and that implies m is 0. Okay. So, what Nakayama lemma says is that if you take a local ring and M to be a finitely generated A module, then I m can never be M unless m is 0 for any non-unit ideal. Okay. So, there are as a corollary of Nakayama lemma, one can obtain or equivalent form of Nakayama lemma. Let us look at one or two different versions. So, this is if I m is m, then m is 0. As a corollary, first of all, let A be a local ring unique with unique maximal ideal M. Let M be a finitely generated A module. If N is a submodule of M such that M is equal to N plus mm, then N is equal to M. This looks like a strange form, but this is indeed a very useful form when we try to prove certain equalities of ideals. When we have to prove that if I start with an ideal I and an ideal j which is contained in I, and you want to prove that I is equal to j, one of the methods is to prove that I is equal to j times mi. Okay. This is one way of applying Nakayama lemma, and this has been useful very often, even in the research this is being used. So, this is a quick corollary. Proof directly follows from the statement. So, what we do is, see, we have to prove that m is equal to n, and here we talk about some statement implies m is equal to 0. So, how do you convert it in that format? We want to look at some module, right? It should have a module structure. So, what kind of module? Well, I mean, something is 0 will imply n is equal to m. That is what ultimately we want. So, what should be the module that we should be considering? M minus n is a set, but that does not have a module structure. Take m mod n, right? If you take m mod n, and if you prove that n is 0, then m mod n is 0, then m is equal to n. So, consider the module m mod n. Okay. To say that m mod n is 0, what is that we need to prove? We need to prove that for an ideal contained in the Jacobson radical. What is Jacobson radical in this case? M itself. Contained in m times, that ideal times m mod n is equal to m mod n. Now, let us look at, so here it is the Jacobson radical. Let us look at what is m times m mod n. by definition this is equal to plus n modulo n, right. The quotient is precisely equal to plus n mod n. So, this is a general fact. If you take for any ideal I times m mod n, this is same as I m plus n modulo n. Okay. This is so how do you verify this? Look at the definition of this. What is the definition of this? This is by definition set of all summation ai times mi bar, right. This is finite summation ai coming from I, but this is same as summation ai mi whole bar. But now what is meant by, so this one will tend to express it as Im mod n, but there is nothing like this, right, to say. So, if you look at this, okay, let me explain this because I feel that you are not very comfortable with that. So, it is better not to deal with only with elements. Look at this natural map from M to M mod n. Okay. So, I have this I times M mod n, this is a submodule of M mod n, right. Now, what would be its so this is the natural map, what would be its inverse, phi inverse of I dot M mod n? See, this is a submodule, okay, and certainly this contains 0. So, inverse image will certainly have n there, and this will certainly contain Im because we are taking inverse images of all elements of this form. This is also, we can say this is same as the whole bar, right. So, I have all the elements and n also here. Now, if I take any element here, so if I take any element, for example, if I look at any element in this ai mi bar, what is its inverse? This, the inverse of this is precisely, it's not an element in here because there are, there could be several elements that will be mapped to this one. What are the elements? If I take any ai mi plus n, where n in n, this will be here, right. So, this will be the set summation ai mi plus n, where n is in n, or in other words I can write it as summation ai mi plus n, represented this way, and that is in im plus n. So, what we have shown is that this is contained here. So, therefore, these two are equal. Is this clear? So, that is the solution for this exercise. I times m mod n is nothing but im plus n modulo n. Now, this is by hypothesis, this is equal to mm plus n is equal to m, therefore, this is m mod n. Okay. So, by m mod n is 0, which implies m. Is this clear? We are taking m times m mod n by exercise, this is equal to m plus n mod n, but the hypothesis is that m plus n is equal to m. Therefore, this is equal to m mod n, but then we have m which is contained in the Jacobson radical, which is equal to the Jacobson radical, with the property that m times the module is equal to the module itself. By Nakayama lemma, m mod n, the module is 0, m mod n is 0, which means m is equal to n. Is this clear? Another nice corollary of Nakayama lemma is in talking about something similar to a basis. See, in the case of vector spaces over a field, there is any minimal generating set and maximal linearly independent set, they all have same cardinality, or any two minimal generating sets have same cardinality, right, that is linearly independent, we have basis and so on. But we have seen that in the case of modules that is not necessarily true. There can be two different minimal generating sets of different cardinalities, but if we are in a slightly nicer situation than just a commutative ring, then we still have something nice. So, let us look at this, let AM be a, so this is a standard way of denoting. When I say AM be a local ring, it means A is commutative ring with identity and it is a local ring with M being the unique maximal ideal and M be a finitely generated A module. Okay. Now, if I look at, then if I look at this module, okay, M is exactly the annihilator of this module. The maximal ideal M is precisely the annihilator of this module, right, and therefore this is a vector space over A mod M. A mod M, I mean it is a module over A mod M, which is same as saying vector space over A mod M, because A mod M is a field. Then this is a vector space over A mod M. Can we say that it is finite dimensional? Can you see that it is finite dimensional? Okay, so this is one remark. Let M be a finitely generated A module and I in A be an ideal. Then we know that M mod I M is an A module, at least to start with. Can you say something more? Is it finitely generated? Will this be a finitely generated A module? Because M is, I am saying that M is finitely generated A module, which means, see what am I saying, M is equal to, I can find a set, there exists M1 up to Mn in M such that M is equal to summation set of all I from 1 to n ai mi ai in A. M is precisely of this form. Okay. Now, if I take this as an A module, what are the elements? They are equivalence classes of all elements of this form. So, in particular, can you get me a generating set for this as an A module? Mi bar, like M1 bar, M2 bar up to Mn bar will be a generating set for M mod Im as an A module, right? Can you say, okay, so this is a finitely generated A module. Can you say something more? M mod Im is an A mod I module, right? Can you say this is a finitely generated A mod I module? Will the same generating set will M1 bar up to Mn bar generate M mod Im over A mod I? Yeah. See, if you look at the multiplication here, we are taking linear combinations with elements in A. Now, I is contained in the I is equal to the annihilator of M mod Im. I is contained in the annihilator, because you know there could be other elements that annihilates M. So, I plus annihilator of M will be equal to the annihilator of M mod Im. So, I is contained in the annihilator, therefore, if I take any element from I, those linear combinations will certainly become 0, it will vanish. So, if you take two elements which are same modulo I, their product and their summation etc. will give you the same element, which means the same set will generate m mod I m over a mod I. So, the answer here is yes. So, what have we proved? We have proved that m mod I m is a finitely generated a mod I module. So, if M is finitely generated A module, then M mod I m is a finitely generated A module. Not only that, M mod I m is a finitely generated A mod I module. Okay. And we have not only proved that, we have proved that if I take a generating set of M, the same set, from the same set I can get a generating set for M mod I m as an A module as well as an A mod I module. The same set will generate. Okay. So, now let us return to our situation. So, M is a finitely generated A module, therefore, M mod M m is a finitely generated A mod M module, but A mod M is a field, therefore, M mod M m is a vector space over A mod M. Not only that, it is a finite dimensional vector space. So, this and M mod M m is a finite dimensional vector space over A mod M. So, it has a basis. So, let us take M1 bar up to Mn bar be an A mod M basis for M mod Mn. Okay. So, what would, though one cannot, can we expect this will generate M? A priori there is no way one can expect this. You have a generating set for a quotient, how do you expect that to generate the whole module? It need not. Okay. So, let us let Ni be maybe I will just write this Mi be a pre-image of Mi bar. So, when I say pre-image in the natural map. Okay. Let N be the submodule generated by M1 up to Mn. So, my question is whether N is equal to M or not. I mean, to start with, we cannot really believe that it is. So, let us see. So, I have this submod, N is a submodule of M. Okay. If M is
generated by MIs,
yeah,
then it's enough, because any generator which
yeah,
is not MI bar will have to be in MM.
this will not contain all these Mi, right, because there is huh.
No, I am saying that if M1 to Mn is not a generating set, then it will any generating set will
there will exist some element. No, see, we might have something in between n and m. So anything here will become 0 when you take quotient.
Yeah.
So this won't matter at all, right? I didn't understand what.
I'm saying that that is the generating set for m mod n.
Yes.
If there is some other element apart from mn, mi's
Okay.
in the generating set,
Yeah.
then it should belong to mn.
Yeah, it should belong to.
Mi's to a generating set.
Yeah. So, or in other words, see, what you are trying to say is that if I show that this is m, right, that is precisely what you are saying. And this is what we wanted to show. I mean, if we show this, then we are done because of the corollary of Nakayama lemma, right? Very good. Now, is this true? Let us look at. So, m mod, so this is n is a submodule of m. What is the image of, what is the submodule of the images of elements of n in m mod mm? Submodule of m mod mm generated by images of elements in n. What is this? What is n? N is the module, submodule generated by m1, m2 up to.
It is equal to m mod n.
This will be equal to is m mod mm, right? Because n is generated by m1, m2 up to mn. So if you take its images here, its images precisely the module or the vector space m mod mm. Now if I look at the natural map, what is phi of n? What is phi of n here? If I take any submodule, no, how do you, so okay, this is a general question. Suppose I have k be a submodule of m. So this is exercise. K be a submodule of m, okay, and phi from m to m mod k is the natural map. If n is a submodule of m, then phi of n is equal to, can you give me a precise representation for this in m mod k? It's the exercise is very similar to the way we proved m mod im n plus k mod k, right? It's precisely n plus k mod k. So therefore, let us apply that here. What is the image of n here? The image of n is, so now let phi from m to m mod mm be the natural map, then phi of n is equal to n plus mm mod mm. Therefore, but image of this is equal to, we know that this phi of n is equal to m mod mm, because images of m generates m mod mm. So, this is equal to, this implies m mod mm is same as n plus mm mod mm, or in other words this mod this is 0, but what is this mod this, which is isomorphic to, this implies m mod mm modulo n plus mm mod mm is 0, but what is this? This is isomorphic to m mod n plus mm is 0, which implies m is equal to n plus mm. By the corollary of Nakayama lemma, this says m is equal to n. So, what have we shown here? We have shown that if I take an a mod m basis of m mod mm, this number, this set will generate m1 up to mn, this will generate the module m, the corresponding inverse images will generate m. Note that during the whole proof we did not use that this is a basis, we only use the property that it generates, right. So, now suppose this, and we take, suppose this is a basis, basis means it is a minimal generating set, right. Now, what can we expect? If this is a generating set for m mod mm as an a mod m vector space, then we have proved that this is a generating set for m as an a module. Now, I am saying this is a minimal generating set, or it is a basis. Can we expect this to be minimal? Let us go through the proof. Let us see whether we can. Suppose this is not a minimal generating set. What does that mean? It means that there exists one of the MIs which can be written as, which can be obtained from others. This is, when do you say a set is not a minimal generating set? Minimality is with respect to the inclusion. So, if this is not a minimal generating set, that means there exists a subset which is a minimal generating set, which is a generating set. So, I can find at least one MI which is written as a combination of others. So, let us say Mn is written as linear combination of M1 up to Mn. Now, take its image into m mod mm. The coefficient of Mn will remain non-zero, at least that will remain non-zero. So, you have a linear combination of basis elements that leads to 0, which is a contradiction. So, we have proved that if this is a basis for m mod mm over the field a mod m, then this is a minimal generating set. We do not use the terminology basis because we do not have linear independence here. What we have shown is that this is a minimal generating set. Now, over a local ring, this uniquely determines the number of elements in a minimal generating set, right. So, any minimal generating set will have this dimension of this over this number of elements. So, therefore, one can define the term, we do not have dimension in the case of this, we do not have the definition of linear independence, but we do have minimum a minimal cardinality of a minimal generating set. Okay. So, therefore, this is mu m, this is cardinality of a minimal generating set, minimal generating set. This is a well defined terminology when you have a finitely generated module over a local ring. Okay. This is one of the most important applications of Nakayama's lemma. So, now let us move on to study exact sequences. So, we saw, we have been dealing always with a homomorphism. Okay. Suppose I have a sequence of homomorphism mi to mi minus 1 to mi minus 2 be a sequence of homomorphism, A module homomorphisms. So, this is, I will denote this by fi, fi minus 1 and so on. Each of them is an A module homomorphism. Okay. This sequence is said to be exact if image of fi is equal to kernel of fi minus 1 for all I. So, I can have sequences of long sequences of modules in homomorphisms. Let us look at one or two simple examples. What is meant by this is exact? Kernel f is image, which means which is 0. For any module A modules n and m, this is exact if and only if f is injective, right. This is exact if and only if f is injective. Now, can you formulate kernel should be image. What is the kernel of this map? Whole of M. This is onto. So, this is exact if and only if F is onto. Let us look at some precise examples. So, this is one of the most basic important examples in the area of commutative algebra. So, I take my ring to be Kxy, okay, and look at this exact sequence 0 to A direct sum A to 0. Now, what is this map? This is y minus x, and this is x y. I am writing this the matrix. So, or in other words, here A is mapped to ay minus ax, and any Rs is mapped to so here okay, I am representing as in the case of vector spaces and so on, we always whenever we have to write this as left multiplication, we write this as the vectors as column vectors. Okay, I am following the same convention. This should be Rx plus Sy. Yeah.
Why you not define ordinary inclusion and projection?
Sorry.
Is basic inclusion of A goes to A comma 0 and that is projection on the first one.
Yes. So okay, very good. So if I look at this A to A direct sum A to 0, x mapping to x 0 and AB mapping to B, right? Kernel should be the image.
That is a particular case.
Sorry?
That is a particular case of this.
Exactly. So here what is y and what is x in this case? But here this is the ring A. Well, these two are slightly different. Here I am talking exactly about the variables, not really y equal to and so. This is yeah, one of the natural examples I could have mentioned early before this, but this is this example has much more. If you study commutative algebra further, this is one of the most basic example of a resolution of these two elements, the ideal generated by x comma y. Okay. This is something that you will learn if you do an advanced course in commutative algebra. Okay. But this is an interesting example by itself.
Why that is not a special case of this one?
These are variables, y and x are simply variables.
So taking a special value for these variables, we will make this a special case.
No, if you take x equal to 0, the ring changes. Ring is no more A. This is for any commutative ring. You take any commutative ring, this, but in this case if you put x equal to 0, the ring is different. So here one can easily see that this is I mean this is an exact sequence. So, this is injective and this is surjective, and kernel of this is same as image of this. So, this is, I will leave it as an exercise. We will continue